Hello everyone, welcome to this new MOOCs course on the topic of applied thermodynamics for engineers. This is start of a new season, the first lecture, so I am really excited about what we are going to have in the following 12 weeks. I am sure that I can make this course interesting to each of you, and it is your participation that is going to make it a fun affair instead of being a hard taught subject like thermodynamics. Now, to start with, I should introduce myself first. I am Dipankar Basu, an associate professor in the Department of Mechanical Engineering, IIT Guwahati. I received my formal education firstly from Jadavpur University, Kolkata, and then doctoral research from IIT Kharagpur. I am here in this large green campus of ours from 2012 onwards. Now, here in the Department of Mechanical Engineering, I belong to the fluid and thermal specialization, and accordingly I am associated with teaching fundamental courses like thermodynamics, fluid mechanics, heat transfer, applied thermodynamics, also master's level courses like two-phase flow or nuclear power generations. And this is actually not the first MOOCs course that I am doing. I have done MOOCs course earlier also, but this is my first attempt with applied thermodynamics. And I am really happy to be here because thermodynamics is a subject that is my all-time favorite right from my college days. I have always been a big fan of thermodynamics, the basic thermodynamics, and also the application of that to different engineering fields. And I have also taught this subject several times here at IIT Guwahati to the second year BTech students, and therefore I am very much confident about what I am going to offer to you. Now, before I start any discussion regarding the course, there are a few things that I have to mention. Firstly, the course is on applied thermodynamics. So, basic thermodynamics is a prerequisite to this particular course, and the thermodynamics is generally taught in the first or second year of any mechanical engineering course, because without thermodynamics you can't learn courses like fluid mechanics or heat transfer. Therefore, if you belong to the second year or third year of your mechanical engineering, you must have already done the basic thermodynamics, and that background of basic thermodynamics is very important, because what are the laws of thermodynamics, how to apply those laws in different engineering applications, you must have proper grip on that, and then only we can go for the analysis of different kind of thermodynamic systems or engineering systems from thermodynamic point of view, which is going to be the scope of this particular course. And also a word of caution, as I have done MOOCs course earlier, from there I can say that while the idea of MOOCs is very encouraging and very interesting, but the biggest hurdle that the students generally faces, and not only students, in fact as being an instructor, the biggest hurdle for me is the lack of direct communication. Here I am not able to teach in a live classroom, rather what I have is only this monitor and the camera in front of you, and all of you are on the other side of the camera, and therefore only communication that I can have with you is just whatever I am saying here, and accordingly whatever feedback I am going to get from you. Had it been a live class, I can immediately understand after explaining a particular topic if I want to, or if I need to go a bit further on that, if I need to repeat the discussion, or I can continue. But here I don't have that option. Whether a particular topic has reached you or not, I can understand that only after getting the feedback from your side, and therefore your feedback is very important. Please regularly use the portal of this particular course, and whatever you are gaining from this course, whether you are getting the concepts or not, if you have any query, whatever you have in your mind, please write to the portal so that I can immediately communicate to you. And also, in order to have a better communication, and for the sake of better understanding for on your side, I think we can follow two things. Firstly, the first part is yours, that is, as I have just mentioned, you need to give the feedback immediately to me. If you have understood the topic, please let me know that. If you have not understood anything, please write that doubt to me so that I can clarify that. And it's only after getting your responses I can think about repeating any particular topic or giving some more examples, or maybe approaching a topic in a different way. And also I am planning to have a few live sessions where I can directly interact with you through Hangout, but of course that depends upon the logistics. And the second point that falls on me, I would try to go systematically and slowly through this course. In fact, it is quite difficult to teach any fundamental subject like thermodynamics or fluid mechanics through slides, and I am not at all a big fan of that. Therefore, I am going to treat this one more like a classroom lecture with just a plain blackboard, so that I can derive everything here. Every small concepts I can discuss in detail, every bit of mathematics I can work out here, and therefore, you may not get too many slides here, rather there will be more number of empty slides where I am going to write the things I am going to discuss from very scratch. Only big pictures which are absolutely essential, or some big points which with which I have to start the discussion, that probably will be available on the slides. I would like to go systematically, slowly and in detail to every bit of concepts. So, now let us begin our discussion, and firstly we have the course outline. You by now you must be knowing that it is a 30 week course, or I should say 30 lecture course. That is, the entire content of this course has been divided into 12 modules. Each of the module will be covered in a separate week. So, we are planning to have 12 weeks of series of lectures, and this is how I am planning to go. The first module, that is right from this lecture and following 2-3 lectures, we are going to talk about the review of thermodynamic principles. This is more like a review of what you have done in basic thermodynamics. Now, I have already mentioned that thermodynamics is a prerequisite for this course. So, you may be thinking what is the need for this one, but the issue is that, okay, before telling the issue, I would like to thank you because of the large number of responses I am getting in terms of the registration to the course, and that also shows a good variety among the registered students. Now, when there are such variety among the registered students, then I feel it is important to have a review of the basic thermodynamics, because in different places thermodynamic concepts are explained following different standards, different approaches, different textbooks, and therefore, it is important to assimilate all of them into a common basic platform, so that you can understand exactly what kind of conventions I am going to follow here, what kind of symbols I am going to follow here, and exactly what kind of interpretation of thermodynamic laws I am going to make use of. Therefore, in this first week I am going to review the basic thermodynamics, where we are going to discuss basically everything, starting right from thermodynamic states and properties, defining the thermodynamic system, the concepts of energy interaction in the form of heat and work, then the first and second law of thermodynamics, and very important, the concept of entropy and exergy. Then next week I am going to talk about the thermodynamic property relations. As you will be seeing shortly, you see from the thermodynamic state postulate that if we know two independent intensive properties, we can calculate any other property. But how to calculate that you will be learning in this second week, where we shall be starting with the Maxwell's relation, then developing generalized relations for changes in internal energy, enthalpy and entropy for ideal and real gases, then Clapeyron relations and Joule-Thomson coefficient. Then properties of pure substances, it is also generally followed or covered in most of the basic thermodynamics course. But still I shall be reviewing the phase change process, corresponding T s and H s diagrams, then ideal gas equation of state, concept of compressibility, and real gas equation of state, which you may not have already learned. Then the more relevant topics to apply thermodynamics, like the air standard cycles, which is the ideal cycle for the reciprocating engines. So, we shall be analyzing the Carnot, Otto, diesel and dual cycles, Stirling and Ericsson cycles. Then the application of these air standard cycles to real engines. So, we shall be talking about the real cycles for reciprocating engines in terms of fuel air cycles, and following different kinds of losses in actual cycles. Then moving on to the gas turbines, the ideal Breton cycle, intercooling, reheating and regeneration, possible improvements and modification in the Breton cycle. Then moving on to the vapor power cycles, where you must be knowing about the Rankine cycle. So, we shall be starting with the Rankine cycle, then incorporating the reheat and regeneration concepts on that, possible improvements in vapor power cycles. Then the combination of gas turbine and vapor power cycles in cogeneration and combined cycles. Then in week number 9, we shall be talking about the refrigeration cycles, where ideal vapor compression and abrasion refrigeration cycles will be coming. We shall be talking about different kind of refrigerants. Then the gas mixtures, properties of ideal and real gas mixtures, reversible mixing process and second law efficiency. Finally, the gas vapor mixtures, which is associated with air conditioning. So, we shall be talking about the properties of moisture, psychrometry and psychrometric chart, analysis of different air conditioning processes, the concept of comfort, and very basic discussion on the components of a standard air conditioner. And finally, I would like to round off with a brief idea on chemical thermodynamics by discussing about the combustion process, concepts of enthalpy of formation and enthalpy of combustion, adiabatic flame temperature, and the first and second law analysis of reacting systems. So, you can see from the syllabus is a quite involved course, quite heavy course in a way, because we are trying to cover almost all the aspects of applied thermodynamics in several places, like right here at IIT Guwahati we generally have 2 applied thermodynamics course, or we used to have 2 applied thermodynamics course, now that have been combined into one for BTech students, and we are having more or less a similar kind of syllabus here. One topic which is not explicitly mentioned here, that is reciprocating compressors. Somewhere I would like to discuss a bit about reciprocating compressors also, probably in conjunction with the air standard cycles, because analysis of reciprocating compressors are quite similar to the air standard cycles, and also the concept of compressor is very important from air standard point of view. Now, some of the topics in a particular week will be covered in 3 or 4 lectures, where some of them may need just 2 lectures. So, overall we may be having a total of 36-37 lectures. Yes, like just in this first week itself, the review of thermodynamic principles is going to take 4 lectures, whereas some others like probably this module number 5 is going to take only 2 lectures. So, let us see how we can proceed. These are the textbooks that I have already mentioned in the course web page. The first 2 are the standard thermodynamics books, the book of Sengel and Bowles I am going to follow the most, and also the classical book of Sontag. Here I have given a very old edition, but the much newer edition is also available to this particular book. Sontag and the book of Sengel and Bowles that will be suitable for most of the basic topics that we are going to talk in this course. However, in certain cases you may have to look into different books, like the book of Estop and McConney is a book specific for applied thermodynamics. This one also I shall be using for certain discussions, and though I am not mentioned here, but for certain other topics I may have to use some specialized books, and I shall be mentioning that during those discussions, like the topic of when we shall be talking about the reciprocating engines or air standard cycles, then I may have to use or refer to some books of IC engines, whereas while talking about the refrigeration cycles I may have to refer to the books of refrigeration and air conditioning. So, I shall be referring to those books suitably. Now, let us start the coverage of this particular week, and this week we are going to talk about the, or basically we are going to review the basic thermodynamics course, which you have already done in just 3 or 4 lectures. So, though I have mentioned that I am going to go slowly in this course, but this week I probably have to go a bit quickly, because whatever I am going to talk about you are expected to know each of them. So, this is more to brush up your earlier knowledge and also to make it conversant to the conventions that I am going to follow in this course, and also the approaches of analysis that I am going to follow in this course. Those of you who have already done the assignment 0 may have already seen may have already faced questions similar to the one that we are going to talk about in this week. So, any discussion of thermodynamics starts with the definition of a thermodynamic system. So, what is a thermodynamic system? A thermodynamic system is classically defined as a quantity of matter or a region in space where we are going to focus to perform any kind of thermodynamic analysis. So, the choice of system right from the definition you can see that it is upon us, or it is upon the person who is doing the analysis. We can choose any system suitable to the situation that you are dealing with, and even for a given situation you may have different choices for the system depending upon what you are actually looking to identify. Depending on the choice of the system, the nature of analysis may vary, the nature of different interactions may vary, and therefore, the choice of system is extremely important for any kind of thermodynamic analysis. Like just shown here, it is a rough system where you can see the blue portion is the system that I am talking about, which we have selected for performing certain kind of analysis, and therefore, we have separated out from the rest by using this purple line. So, this purple line is the one that is referred to as the system boundary. So, anything outside the boundary is called surrounding. Anything outside the boundary is called surrounding, and therefore, boundary can be viewed as the barrier between a system and the surrounding, and any kind of interaction between a system and surrounding takes place across the boundary. Like shown here, across the boundary we may have mass moving into the system or going out of the system, energy may be moving into the system or moving out of the system, but these are the type of interactions the system may have with the surrounding in form of mass or in form of energy, and all these interactions are recognized at the boundary of the system itself. So, immediately you can see that from the definition of the thermodynamic system, we can probably have two kinds of system. One, quantity of matter, or region in space. So, accordingly systems are classified into two classical categories: closed systems and open systems. Closed systems refers to a quantity of matter, where we are talking about a fixed amount of mass, and therefore, we often call them control mass. So, here we have fixed up a quantity of matter, a fixed quantity of mass that we are talking about, and therefore, across the boundary of the system there will be no mass interaction. There will be only energy interaction between system and surrounding, but there will be no mass interaction, because if there is any kind of mass interaction, the mass of the system tends to change, which we can't allow as per the definition of a closed system. So, for a closed system we can have, or if we write this way, energy interaction and mass interaction. For a closed system we can have energy interaction, but no mass interaction. Accordingly, we call them a control mass system. Other one is the open system, where we take the second definition, a region in space, where in space we identify a region and perform the analysis for that given space. So, accordingly, we often call them a control volume system, because we are often talking about a fixed volume in space. So, the boundary of the control volume system always gives away specific volume. So, for a control volume system we definitely can have energy interaction between system and surrounding, and we can also have mass interaction, because here we do not have any restriction about a fixed quantity of mass, but the volume has to be constant. Now, the boundary of the system can be of different kinds of natures, like the boundary of the system can be rigid or elastic, that is movable. Boundary of a system can be real or can be imaginary. So, that depends upon our choice. Like just think about a closed system. In case of a closed system we are talking about a fixed quantity of mass, but we are not telling anything about the volume. Then the volume of a closed system can change, and volume change means the boundary will be moving. Like suppose if we are talking about this rectangle as our system, if this is a control mass system, that is a closed system, then with any kind of energy interaction the boundary of the system may change. Okay, let me take the example of, let us take the example of a hot air balloon. We have a hot air balloon where the boundary, this red line actually is the rubber material which forms the surface of the balloon. Inside the balloon you have some hot air, and outside you have the surrounding. Now, using some source, maybe a Bunsen burner, we are adding heat to this to the air which is present inside. Now, as energy is added to the system, then what will happen? The temperature of the gas, the hot air which is stored inside the balloon, the temperature will increase. Because of the increase in temperature, the volume of the gas will also start to increase. What kind of system is this one? This here we are talking about a given quantity of mass of air inside the system. So, it is a control mass system, and this red line is the boundary of the system. But on supply of energy, the volume of the system can change. Accordingly, the volume of the balloon may change to something like this. Therefore, it is not a rigid boundary, rather it is a movable or elastic boundary. Therefore, for control mass system we may have, or we generally can have, movable or elastic boundaries. However, if we take the situation of a rooftop water tank, this is a standard rooftop water tank, maybe made of brick, maybe made of some hard say plastic, which we commonly encounter in our houses. So, what we generally have, we may be having a water inlet, through the water comes to this, and we may have one or multiple water outlets. Let us consider couple of water outlets. So, this is our inlet number 1 and this is your outlet number 2 and 3. So, what kind of system is this? Here the mass is allowed to flow into the system and out of the system. So, it can't be a closed system, it is a open system. So, to decide a system whether it is an open or closed, we just have to check whether there is mass interaction between system or surrounding. And now in this case it is an open system, and then what about the volume? The volume of the system as given by this red boundary. Let me now restrict the drawing to or put it in a different way. So, this is the actual hard plastic material that you are having, where this is your inlet side and these are the two outlets. So, here we are talking about enclosing a fixed region in space by this material. So, it is a rigid boundary, because the volume has to be constant. So, the boundary can't move. Therefore, for control mass system we generally have elastic boundary or movable boundary, whereas for control volume system we have rigid boundaries. Now, look at the second type of definition, real or imaginary. Now, in case of balloon, what kind of boundary you have? It is a real boundary or you have to imagine a boundary? Definitely there is a real boundary, because you can see the boundary which is enclosing the mass that you are talking about by this rubber material. So, you are having a real boundary. What you are having in the second situation? In the second situation, you may be thinking that you definitely has a real boundary because there is a hard plastic material. I fully agree, but or I not agree fully. I agree to it you partially, because here though the boundary is there, but that boundary is not enclosing entire of your system, because in certain part, like in this particular part, in this particular part and in this particular part, here you actually have to imagine the boundary of the system. Actually these parts were open and you are imagining certain lines to close the system, and therefore, here the boundary is partially imaginary and partially real. So, accordingly the boundary of a system can be real or imaginary and rigid or elastic. In certain textbooks there is third type of system is also defined, which is called an isolated system. An isolated system is just a special case of a closed system where there is no energy interaction as well. Therefore, for an isolated system both mass and volume remains constant, and therefore, it can be considered to be a special case of closed system. There is no interaction at all between the system and surrounding, and no interaction at all across the boundary of the system. Quite a few examples of systems are given here. Look at the first situation. Here you have a bottle partially filled with certain liquid and heat is being added to this or removed from there. Now, as the top of the bottle is open, then with addition or removal of heat, there may be movement of water vapor or certain other gases across the boundary of the system. So, in this case, what kind of system is this? It is an open system, because we are having mass interaction. And also what kind of boundary you are having? We are having it is an open system, and we are having a fixed volume, that is rigid boundary, but boundary is real apart from this small part. This part we are assuming an imaginary surface to close the boundary from thermodynamic analysis point of view. So, partially it is imaginary. Now, we are closing the bottle mouth using a cork. Now, what is happening? There is no mass interaction at all, mass is not allowed to come in or move out, and so because of the heat interaction, the energy content of the system will keep on increasing, but the mass will not change. Actually, because of heat interaction, energy content may increase or may decrease depending upon the direction of heat transfer, but there is no mass interaction, and therefore, it is a closed system now. Here the mass remains constant, and also for this specific case, if the bottle is made of something like glass which has negligible thermal expansion, the volume also may not change significantly. Now, look at the third situation. It is somewhat like a thermoflask. Here the bottle is not only closed, but it is also insulated. therefore no thermal interaction, no heat interaction is taking place. So, this is an example of an isolated system. Let us take a few practical examples. Just a hot cup of coffee maintained at 70 degrees Celsius and kept in a cold environment of 20 degrees Celsius. Then what will happen? Because the coffee cup is at a higher temperature, or coffee is at a higher temperature, it will lose energy to the surrounding. Also the top is open, so you can find there is a heat interaction, and also as the top is open, the water vapor may start to move out. So, it is an open system and it is a control volume system, where you are having this coffee wall and also an imaginary surface at the top forming the boundary. A standard medical thermometer. Now, what kind of system is this? Here you have to choose the system boundary first. That is important, because in the previous examples there is a proper boundary given, but here you have to choose the boundary. So, what can be your choice for the boundary? Here you are having the capillary tube through which the mercury or whatever thermometric fluid you are using, that is present. So, that itself can be taken as the boundary. So, accordingly your choice of your boundary of the system can be this yellow capillary, which is forming this particular surface. So, this one may be the boundary of the system, which encompasses only the thermometric fluid part. Now, when you take this thermometer in contact with our body, there will be some kind of energy interaction. So, it is not an isolated system, energy interaction is taking place. Now, is there any mass interaction between system and surrounding? Because the boundary we have drawn, and it is a rigid boundary, a real boundary. In this case, you do not have to imagine the boundary, because the capillary tube has a fixed wall. So, there is no mass interaction, mercury or whatever thermometric fluid you are using, that is not allowed to come outside this capillary tube, and so it is an example of a closed system. What about this one? You have a piston cylinder arrangement, where the connecting rod, because of the connecting rod, the piston is continuously moving inside the cylinder. So, we have to choose our system now to analyze the thermodynamic behavior of the gas which is enclosed in this cylinder. So, your choice of system can be something like this, that is the side walls plus the top of the piston plus the cylinder head together can form your cylinder or form your the system. This is a real boundary that we are using, but a movable boundary, because the piston is continuously moving up and down. So, it is a movable boundary, but movable real boundary. But what kind of system is this? Closed or open? There is no inlet outlet shown. So, there is no mass interaction. So, this is an example of a closed system with real movable boundary. And my final example is human body. What kind of thermodynamic system or human body can be seen as? If we consider our skin as the boundary and everything inside that as a part of the system. So, everything outside the skin is the surrounding. Then what are the kinds of thermodynamic analysis we can have, thermodynamic interactions we can have? Of course, because of the respiration, we have air coming inside our system and also going out. So, it is actually an open system, because there is a mass interaction. There are several kinds of thermal interaction and energy interaction can take place, because of convective heat loss to the surrounding, we may be losing energy to the surrounding. There may be conduction through the part of our body which is in contact with the ground. There may be radiation losses under certain situations, particularly through the clothing that we are wearing. Also, when we sweat, some sweat may evaporate from our body, that also leads to another source of mass interaction. So, it can be viewed as an open system. So, once we know about a system, or once we define a thermodynamic system, now we have to identify the properties of the system, and properties are defined as any quantifiable characteristic of a system. The term quantifiable is important here, because if we talk about something like color, that can't be quantified, that is more a relative kind of identification, and therefore, that can't be identified as a property. Quantifiable characteristics, we have to, any kind of quantifiable characteristic can be a property of the system, like pressure, temperature, volume, energy content, thermal conductivity, viscosity, acceleration, velocity, elevation, all these are different properties of the system, because each of them can be used to define the system under certain situation, and each of them can be quantified. You must be knowing that properties are of two types, intensive and extensive. Intensive means the properties which are not dependent on the size or mass or volume of the system, whereas extensive refers to the properties which are dependent on the size or mass or volume of the system. So, several examples of intensive properties can be temperature, pressure, etc. Whereas examples of extensive properties, mass is the biggest example, most suitable example. Also we can have the energy content of the system, we can have volume of the system itself, and several others will be coming in. As you have studied basic thermodynamics, you must be knowing concepts of enthalpy, concepts of entropy, all these are extensive properties. Now here comes one important convention that we are going to follow and also corresponding exceptions. Generally extensive properties are denoted with capital letters like this: capital E, capital V, capital H, capital S. This refers to extensive properties, with mass being an exception. Small m is used for mass, but that is an extension, that is an exception. Extensive properties are always referred by capital letters, whereas intensive properties are generally referred by small letters, though temperature and pressure are exceptions. T and P are exceptions, but other intensive properties are generally referred by small letters. Now, how to identify whether a property is intensive or extensive? The easiest way is to see how much is the change in, or whether there is at all any change in the value if we divide the system into two equal halves. Just like the example shown here. Here I have given you a system which is for which we know 5 different properties. M is mass, the volume, temperature, pressure, and rho, the density. Now, if we divide the system into two equal parts, if we divide the system into two equal components and check the properties of those two individual systems, then what will happen? Temperature, pressure and density will remain the same, but mass and volume will become half. So, these three are intensive properties, whereas these two are extensive properties because they are dependent on the size of the system. So, density can be another term which we are going to use rho for density, that is another important intensive property. Now, any intensive property, or I should say any extensive property per unit mass is called a specific property. Like volume is an extensive property which we are going to use capital V for this. If we divide capital V by mass, then we call this specific volume. So, specific volume is volume per unit mass. Similarly, we can define any specific version of any extensive property just by dividing it with mass. Now, the specific version of any extensive property is an intensive property. Just think about the example that I have here. Here, what was the specific volume for this? It was specific volume for the original system was V by M. Now, look at the two components. For this one, what will be the specific volume? Half V divided by half M, that is equal to V by M, which was the original one. Similarly, for the second case also, you are going to have V by M. So, specific volume actually is an intensive property, and therefore, we are going to denote this one by small v. Capital V refers to the volume, the extensive one, small v will refer to the specific volume or intensive property. Similarly, any extensive property per unit mass is an intensive property. So, if capital S refers to an extensive property, capital X per unit mass will be given by small x, which is the intensive version. Accordingly, we can define, say, small h, the specific enthalpy, as enthalpy per unit mass, small s specific entropy as capital S by M. We can define small e as specific energy, capital E by mass, small u specific internal energy as capital U by mass. Can you think about any other examples of intensive properties? Okay, what do you think about velocity? Velocity is an intensive property or extensive property? Just think about that way. Let us say c is the velocity of the original system. Now, if I divide into two components, what will be the velocity for each part? It will remain c in both the cases, therefore, this is an intensive property. What about acceleration? Similarly, acceleration also is an intensive property. So, this way any property can be identified as either extensive or intensive, and also you have to remember that the specific version or per unit mass version of any extensive property is an intensive property itself. And also, as per the convention, we are going to use the small letters to denote intensive properties and capital letters to denote extensive properties, exception being mass, where we are going to use small m despite it being an extensive property, and pressure and temperature we are going to use capital T and capital P respectively despite them being intensive properties. Next is state. State is the exact physical condition of a system. So, to know the exact physical condition of a system, we have to specify all the properties that are relevant. Once we know all the properties of a system, then we can say that we know the state of the system. And in thermodynamics, we always deal with equilibrium state. Equilibrium state refers to a state of balance, that is a state where there is no unbalanced potential inside the system, because of which the properties are not changing. Or I should say that if a system is in thermodynamic equilibrium, then there is no unbalanced potential inside the system, and therefore, the properties of the system are not changing with time. All the all may not be also changing with space, as I am coming to that. But in thermodynamics, we always deal with the state of equilibrium. Even if the system is not in equilibrium, we try to reach a situation where it is very close to equilibrium, so that we can assume it to be in equilibrium and accordingly perform the analysis. So, to know the equilibrium state of a system, we need to know the values of each of the properties which are of importance to us. And equilibrium can be defined from different point of view. We can have thermal equilibrium, which is associated with the equilibrium of temperature. A system is in thermal equilibrium means temperature is same everywhere, so that there is no thermal potential in the system, and hence there is no net heat transfer is taking place from one part of the system to another part. Just see, if this is your thermodynamic system, and here at one part your temperature is T1, another part temperature is T2. Now, if T1 is greater than T2, then we know that there will be some kind of energy flowing from T1 to T2. Then this system is not in thermal equilibrium. If the system is thermal equilibrium, then we can't have any such kind of internal heat flow, and therefore, these two temperatures has to be equal to each other. Otherwise, the equilibrium or thermal equilibrium is not established. Next is mechanical equilibrium. Mechanical equilibrium is associated with pressure, but here we have a difference. A system is in mechanical equilibrium does not mean that pressure is same everywhere, because just think about, say we have a tank of water where this is the free surface of the water and it is filled with certain water having an elevation of h. So, the pressure at this particular point and the pressure at this bottom surface, are they going to be same? They are not same. You have already learned fluid mechanics, and from there you know that hydrostatic pressure varies with the elevation. So, if the pressure that is acting at the free surface is P atm, then the pressure which is acting at this bottom surface will be atmospheric pressure plus rho g h, where rho refers to the density of this liquid and g is the acceleration due to gravity. So, there is a continuous pressure variation, like if we plot the variation in pressure with height, then at this point you may be getting a triangular profile like this, where the pressure is atmospheric at the upper surface and continuously increasing to reach to this particular level at the lower surface, and this is perfectly logical. This system is called to be in mechanical equilibrium because here the pressure, though it is varying with space inside the system, but that is to compensate for the body force field like the gravity in this example. And mechanical equilibrium therefore is associated with the absence of any unbalanced forces in the system. Here the forces are balanced because the pressure force and the gravitational force are balancing each other. Third is phase equilibrium. Phase equilibrium refers to the equilibrium of phases. Like if we have a system which is having multiple phases, say for example you have a thermoflask which is filled up with a mixture of liquid water and ice. Now, if the thermoflux is maintained at 0 degree Celsius under atmospheric condition, then ice and water will not be having any kind of phase change, and so the system will be maintained at a phase equilibrium. However, if they are at a different temperature, then depending on the temperature levels, either water will be converted to ice or ice will melt to form water, then the system is not in phase equilibrium. And finally is chemical equilibrium, that is means the absence of any kind of chemical potential, no chemical reaction taking place in the system, and therefore the molecular structure is remaining the same. So, this way we can have 4 kinds of equilibrium situation in a system, and when a system satisfies all these equilibrium conditions, then we call it to be in thermodynamic equilibrium. Therefore, system can be in thermodynamic equilibrium when all these kinds of equilibrium conditions are satisfied. In this course of thermodynamics, we do not have to discuss too much about phase and chemical equilibrium. We shall be primarily considering the thermal and mechanical equilibrium. Chemical equilibrium will be coming into picture only in the last week of this course. It is in the module where I shall be talking about the chemical thermodynamics. Next is the state postulate. As I have just mentioned, to specify the state of a system, we have to specify all relevant properties, and a system can have infinite number of properties, because for every quantifiable properties or any quantifiable scenario we can define a property. Then how many properties we need to define for a system for it to know the state? That is being used by the state postulate, which states that the state of a simple compressible system is completely defined by 2 independent intensive properties. The state of a simple compressible system is completely defined by 2 independent intensive properties. Here we have 2 phrases to be careful of. One is simple compressible system. Simple compressible system means a system which is not being influenced by any kind of external effect, like the system is not being subjected to gravitational acceleration, electricity, magnetism, velocity, or any kind of any such kind of body force field. When it is independent of any such kind of body force field, then we call it a simple compressible system. Whereas the second clause of important is 2 independent intensive properties. The properties has to be independent of each other. Like for a system, if we define say specific volume and density, are they independent of each other? They are not, because we know that specific volume is just reciprocal of density, and therefore these two are not independent of each other, and so specifying these two will not satisfy the state postulate. In most of the situations, generally temperature and pressure are sufficient to deal with this condition of independent intensive properties. However, when you are going for a phase change process, you must be knowing that during a phase change both temperature and pressure remains constant, and therefore from the knowledge of temperature we can calculate corresponding pressure or vice versa. Therefore, in that situation we can take only temperature or pressure, that is one of these two, and we have to specify something else, a second property or a third property I should say, to get 2 independent intensive properties. What can be this third property? That we shall be learning in our module 3 when we shall be talking about the properties of pure substances. But most of the practical situations, particularly when dealing with solids or liquids or non-condensable gases, temperature and pressure are sufficient. But not necessarily that you have to specify temperature and pressure, like temperature and specific volume or pressure and specific volume, or in a certain situation maybe enthalpy and entropy, specific enthalpy and specific entropy I should say, they all can serve this particular condition of 2 independent intensive properties. And if your system is not a simple compressible one, then we have to specify a third property along with the 2 which we have already selected. Like suppose if your system is subjected to gravitational acceleration, then what can be the third property? Let us say this is your datum and your system is located at this particular elevation. So, G is acting downwards and the system is at an elevation of Z. Then the system is having some kind of potential energy, and what is the measure of the potential energy? The potential energy of the system will be equal to mass into G into Z, or if we write in per unit mass sense, then it will be potential energy per unit mass, that is equal to G into Z. Now, G being a constant, this Z is the third parameter that we have to specify to have an idea about the corresponding potential energy. Similarly, if the system is having some velocity, so the system is moving with a velocity c, then corresponding kinetic energy is half mc square, or per unit mass kinetic energy will be equal to half c square. So, we have to specify this velocity as the third parameter. Then the state postulate therefore can also be used for systems which are not simple compressible, provided we specify a third parameter quantifying that additional influence. Next we come to process. Whenever a system is in a state of equilibrium, particularly in an equilibrium with the surrounding, then there is no interaction. However, if the system and surrounding are not in equilibrium, then there will be some kind of interaction between the system and surrounding across the boundary of the system, and that will lead the system from one equilibrium state to another, and that is what we call a process. It refers to the change of a system from one equilibrium state to another. During the process, the system has some kind of interaction with the surrounding, which can be mass interaction or energy interaction or both, and accordingly may not be all, but some of the property values of the system gets modified. We generally represent the processes in terms of property diagram, something like this, where we select two properties, generally intensive properties, independent intensive properties as the two axes, and plot the process. And here state 1 is the initial part of the process or starting point of the process, state 2 is the finishing point of the process, the pink line represents the process path. So, whenever we are trying to represent a process on a property diagram, we generally have to specify three things. Number 1, the initial and final state, like the state 1 and state 2 points are shown here, these are the initial and final states. Number 2, the process path, the pink line, that is the second thing, that is how the initial and final states are connected in terms of the two property that which we have selected as axis, that is the process path. And third, which is not shown in the diagram, is the direction. You have to specify the direction of the process always, because from here if you do not put this direction, then it is not clear the system is moving from state 1 to state 2 or from state 2 to state 1. Therefore, you have to specify the direction of the process, and without this arrow your diagram is incomplete, that is wrong. So, you have to specify three things, state 1 and state 2, that is initial and final states, the secondly the process path, and third the direction of the process. Now, if the system or rather if a process is performed slowly, then it is possible to maintain the equilibrium state throughout the process between the initial and final states. Like take this example of a piston cylinder arrangement. If the cylinder or rather the piston is moved slowly, then say if this is the initial position, this is the initial position of the piston, and these are certain gas molecules which are lying on the piston before you have started to make the piston move. Now, as soon as you force the piston to move, then some additional force is acting on these molecules which are in vicinity to this, whereas the molecules which are far away from this piston, they are not able to sense this one. Therefore, there will be a sudden increase in pressure in this particular zone, whereas the pressure remains the same in other part of the cylinder. So, an imbalance is created and the equilibrium state is not possible to maintain. However, if you move the piston very slowly, so that the whatever additional pressure the molecules are sensing, they are immediately able to transfer that to the surrounding molecules, then the pressure inside the system changes very smoothly, and hence we can identify almost all of the individual states in between. Like this is your this is the starting point, and on application of certain force, if we are doing it slowly, then we can almost identify all these intermediate states, and we can also assume that each of these intermediate states are in equilibrium or at least very close to equilibrium, something we call a quasi equilibrium. Quasi means as if, that is system is very close to equilibrium if not perfectly in equilibrium. And when the system or when a process moves through a series of such kind of quasi equilibrium or quasi static states, then we can easily draw such kind of process diagram. However, if the system is being subjected to a very fast process, then there is an imbalance inside the system, there is unbalanced potential, and therefore system is not able to maintain the equilibrium state, then we can't plot a process diagram like this. Like because say our property diagram, we have selected pressure as one property and temperature as the other property. Now, state 1 and state 2 we know the values of pressure and temperature, but what will be the values of pressure and temperature at somewhere here or somewhere here? If the system is not in a state of equilibrium, then we can't identify these intermediate states, and therefore we can't draw this process path. Then we generally just represent the process by a dotted line, which indicates that we are not sure about the intermediate states. We are just representing this one by connecting state 1 and state 2 with an arbitrary line. Only when the system passes through a series of quasi equilibrium states, then we know all the intermediate states, and therefore we can represent the process path by a continuous line. And when the system goes through a series of processes such that at the end of all this process it comes back to the initial state, then we call that the system has executed one cycle. Like shown here, the system starts with start at point A or state point A, moves to state point B, then moves to state point C, and then from C comes back to state point A. Therefore, there are three processes, A to B, B to C, and C to A, and at the end of the processes the system is back to its initial state. So, we can call that it has executed one cycle. At the end of one cycle, the system returns back to its initial state, and therefore all the property values are restored. Therefore, over one particular cycle, the change in any particular property is 0. That is why properties are called point function. They are dependent only on the state values, they are independent of the process. Just going back to the previous diagram, here our initial state is state 1 and final state is state 2. Now, if the system follows this pink line during the process, or maybe this particular line during the process, or maybe this particular line during the process, the change in temperature will always be the same. The change in temperature will always be T2 minus T1. So, the final values, or I should say the change in any property during a process does not depend upon what path it has followed, just depends on the two state points, and that is why properties are called point functions. And therefore, we can represent this one by an exact differential, can write it as dt. And as during a cycle the system is coming back to the same state, so the change in any property will be equal to 0. So, if x refers to any particular property, then over a cycle the change in that property will be equal to 0. Or in the contrary, if the cyclic integral of any quantity is 0, then that has to be a property of the system, a criteria that we shall be using in the next lecture. And that takes us to the zeroth law of thermodynamics. Zeroth law, though historical point of view came after the first and second law was defined, but conceptually it comes before the first law, and also the concept that it provides can't be obtained from first or second law. Therefore, it is called the zeroth law of thermodynamics. A very standard statement. If two systems are in thermal equilibrium with a third system separately, they are also in thermal equilibrium with each other. Just like this situation, you have a system A and a system B and a third system C. Now, A and B are said to be in thermal equilibrium. Similarly, B and C are also said to be in thermal equilibrium. Then A and C also has to be in thermal equilibrium with each other. If A and C are in thermal equilibrium, then there will be no flow through, no transfer of heat between them when they are in contact. Similarly, there will be no transfer of heat between B and C when they are in contact. So, if now if we bring A and B in contact now, then there also will be no heat transfer between them, establishing that they are in thermal equilibrium with each other. This establishes the concept of temperature and also provides the benchmark or idea of measuring temperature using thermocouple. How can you define temperature without using zeroth law? Because temperature specifically does not have any definition. We can define more in relative sense. This one seems hot, so maybe at a higher temperature. This one seems cold, so maybe at a lower temperature. It is the zeroth law which provides a definition of the temperature. If system A and B are in thermal equilibrium, then some property has to be equal between them, and that property is temperature. Or in a way we can say that for system A and B to be in thermal equilibrium, their temperature has to be equal to each other, or for system A and B to be in thermal equilibrium, the property which has to be equal between them is temperature. Now, if we replace one of the system like the system C with a thermometer, then you have a measurement principle or principle of temperature measurement. Like if object A and thermometer in contact with each other gives this particular level of thermometric fluid, and object B and thermometer also gives the same level of thermometric fluid, then A and B must be at the same temperature. This way, if we set up say object A as certain base, that is something with a known temperature, then we can easily form a thermometer scale, and then taking this object B in contact with this, we can measure the temperature of this object B. Accordingly, we define different kind of thermometer scales. Generally, we use certain standard temperature values, something like suppose if we take ice under standard atmospheric condition, then we specify the temperature to be at 0 degree Celsius, and accordingly we mark that point on the thermometer. Similarly, if we take the steam point, which is 100 degree Celsius under normal atmospheric temperature, atmospheric pressure, then we take steam in or thermometer in contact with steam and mark the corresponding values. And between these two limits, suppose this is your 0 degree Celsius, this is your 100 degree Celsius, in between we form a uniform scale, and from using this thermometer now we can measure the temperature of an unknown object. So, these are the two most common thermometer scales, Celsius and Fahrenheit. As you all know that under the ice point is given the value of 0 degree in Celsius scale and 32 degree in Fahrenheit scale. Now, these numbers we have decided, that you have to understand, it is not that nature has given us these numbers, it is we have decided that in Celsius scale we are going to call the steam point as 0 and Fahrenheit scale as 32, and the steam point accordingly in Celsius scale has been given the mark of 100 degree Celsius and 212 in Fahrenheit scale. So, accordingly any unknown temperature in Celsius scale can be given as we are having an uniform scale formed by this, if unknown temperature is C in Celsius scale minus the steam point which is 0 divided by C minus the ice point which is 0 divided by steam point minus ice point, the two extreme points of the scale, will be equal to the F, which is that same unknown temperature in Fahrenheit scale minus the ice point which is 32 divided by steam point in Fahrenheit scale 212 minus 32, that gives us C by 100 is equal to F minus 32 by 180, that is very celebrated formula, C by 5 is equal to F minus 32 by 9. This way we can easily convert from Celsius scale to Fahrenheit scale or vice versa, and also by knowing the two extreme points we can develop any other temperature scales. Now, these two are relative temperature scales because this choice of steam point and ice point that has been decided by us, and if we are looking for absolute measurement we have to go to the absolute scale, just like the Kelvin scale, where absolute 0 is marked as 0 Kelvin and the triple point of water generally is taken as standard, which we call it given the value of 273.16 Kelvin, and this division between this absolute 0 and the triple point is been divided into 273.16 number of equal parts, with each part signifying 1 Kelvin. So, Fahrenheit and Celsius scales are relative scales of measurement, whereas this is an absolute scale of measurement. And we all know the relation between Celsius and Fahrenheit scales and also the Celsius and Kelvin scales, like any value in Celsius scale will be equal to the corresponding value in Kelvin scale minus 273.15, because the ice point has been given as 273.15 Kelvin in Celsius scale, in Kelvin scale. Similarly, the value corresponding to Rankine scale, which is the absolute version of Fahrenheit scale, that is given as F minus 32 will be equal to R minus 491.67, because 491.67 has been marked as the reference for ice point in Rankine scale. It is for simplicity it has been marked as 270 and 492 in the diagram, but I am giving you the exact value. So, now using this we can easily convert from one scale to another, and here we can write as F is equal to R minus 459.67. So, as we know the relationship between all these temperature scales, we can easily convert one value to the other, and you can also define another temperature scale of your choice. It is up to you that you can take a temperature scale and where you call the ice point a value of 1000 and call the steam point a value of 0 and make an equal division between them. So, here the value will keep on decreasing with the increasing temperature, but it is up to you. If you can make suitable conversion, then that is a perfectly consistent thermodynamic temperature scale. So, that takes us to the end of today's discussion, where we are basically reviewing the basic concepts of thermodynamics. We started with the concept of thermodynamic system, state and properties, processes and cycles. We have seen how to plot the thermodynamic processes on property diagrams. Then we discussed about the zeroth law of thermodynamics, which gave us the concept of temperature. So, the zeroth law allows us to define temperature or define the property temperature as the one which gives the condition for thermal equilibrium, and we briefly discussed about the temperature scales. So, that is it for the day. In the second lecture of this week, we are going to talk about the first and second law of thermodynamics and its application to closed and open systems. Till then, I am signing off. Please go through this lecture, and if you have any query, write back to me immediately. Thank you.